Good afternoon. Today, I'll be presenting our CS350 wireless network simulation project, which focuses on comparing the performance of 4G LTE and 5G NR systems using MATLAB. The purpose of this project was to model and visualize how the signal to noise ratio, or in short SNR, affects core network performance parameters such as throughput, latency, symbol error rate, and cell coverage quality. Through this simulation, we aim to better understand how 5G achieves higher data rates, lower latency, and more efficient communication compared to previously known 4G models. To begin with, let me explain how the MATLAB code was structured. The simulation is divided into several parts, each corresponding to a different analysis. First, we define our simulation parameters. We set the SNR range from 0 to 30 decibels, representing weak to strong signal conditions that we experience. We also specify 10 user devices randomly distributed within a 1 kilometer cell radius to simulate a real cellular environment where some users are close to the base station while others are at the edge of the coverage and some in the middle. We use the interp1 function with the spline and p-chip interpolation to create smooth and realistic curves for our graphs, helping us clearly visualize the trends between SNR and the performance metrics. The first section of the code models throughput versus SNR. Here, we manually define throughput values for both 4G and 5G systems at various SNR levels. For 4G LTE, the values range from 100 Mbps at low SNR to roughly 330 Mbps at high SNR. For 5G, on the other hand, the throughput starts at approximately 500 megabits per second and increases gradually, peaking at nearly 2.7 gigabits per second. These points are then interpolated to generate smooth curves, showing how both technologies scale in capacity as signal quality improves. The next section models latency versus SNR. For 5G, latency begins around 70 milliseconds, and that's for 4G, and gradually decreases to about 45 milliseconds as the SNR improves, reflecting how a cleaner signal allows faster communication. In contrast, 5G maintains consistently low latency between 5 and 7 milliseconds thanks to its highly optimized radio frame structure and shorter transmission time intervals.
The third major section of the code simulates symbol error rate or SER as a function of SNR. We use predefined decay curves to represent how symbol errors drop exponentially as SNR improves. Both 4G and 5G show rapid decreases in SER with rising SNR, but the 5G curve maintains a slightly better performance overall due to advanced error correction codes and high order modulation schemes. Lastly, the code creates a cell map visualization showing the spatial distribution of user devices and their respective SNR values. Users close to the tower have higher SNR, shown in green, while users further away appear in yellow or red, indicating fair or poor connections. This portion of the code also draws the coverage boundary using a dotted circle and categorizes users based on SNR thresholds above 20 dB for good connections, between 10 and 20 dB for fair connections, and below 10 dB for weak connections. Now that we understand the code, let's discuss each graph in more detail starting with the cell map. In this visualization, the black star in the center represents the cell tower, while the dotted boundary indicates the edge of the coverage area. The colored dots represent different user devices. As expected, the users near the center enjoy stronger signals and are marked green, indicating good SNR and high data rates. As users move further away, path loss and interference increases, reducing their SNR and resulting in fair or bad connections, shown in yellow and red. This clearly illustrates the inverse relationship between distance and signal quality, a core principle in wireless propagation. Graph places the user devices randomly every time the program is run. In practice, 5G networks counter this issue. The use of small cells, beamforming, and higher frequency bands to maintain consistent quality even at longer distances. The next graph shows the symbol error rate plotted against SNR on a logarithmic scale. Here we observe that the 4G and 5G experience a sharp drop in error rate as SNR increases from 0 dB to 30 dB. At low SNR levels, both technologies have high error rates because the signal is heavily affected by noise and interference. As the SNR improves, the curves fall exponentially, showing that the communication becomes more reliable. The 4G curve drops slightly earlier because it uses more conservative modulation such as 64 QAM, while 5G initially performs a bit worse at very low SNR since it often uses denser modulation schemes like 256 QAM, which requires a stronger signal to decode correctly. However, once the SNR exceeds about 20 dB, both systems reach extremely low error rates close to 1 error in a million signals, or 10 to the power negative 6, showing that both can achieve highly reliable communication when signal quality is strong. Overall, this plot confirms that high SNR directly improves the accuracy scalability of data transmission. The third graph illustrates latency versus SNR. The blue line represents 4G LTE, and shows latency starting near 70 milliseconds and gradually dropping to 45 milliseconds as SNR increases. The orange line for 5G remains consistently below 10 milliseconds across all SNR values. This difference highlights one of 5G's most significant advantages: ultra-low latency. 5G achieves this through several design improvements such as shorter frame durations, edge computing support, and optimized scheduling mechanisms that minimize delay even in lower signal conditions. This feature is particularly critical for modern applications like autonomous vehicles, remote surgery, and industrial automation, where near real time response is essential.
The final performance graph displays throughput versus SNR. This is where the leap in technology becomes most evident. The 4G LTE curve increases gradually with SNR reaching a peak around 333 Mbps, while the 5G NR curve rises much more sharply and reaches around 2.7 Gbps at high SNR. This improvement comes from 5G's wider bandwidth, massive multiple input, multiple output technology, and ability to operate in millimeter wave frequencies that support much higher data rates. Essentially, as the signal quality improves, both systems transmit data faster, but 5G's efficiency and advanced spectrum utilization allow it to scale almost 8 times higher than 4G. This demonstrates how 5G can handle data-intensive services such as ultra-high definition video, reality, and cloud gaming in case. This demonstrates how 5G can handle data-intensive services such as ultra-high definition video, augmented reality, and cloud gaming with ease. To summarize the findings from our simulation, 5G consistently outperforms 4G in every major metric. Throughput scales up to nearly 2.7 Gbps, providing massive capacity improvements. Latency remains extremely low, staying under 10 milliseconds even in moderate SNR condition. The symbol error rate decreases smoothly with SNR, showing strong reliability for both networks, with, but with 5G maintaining better overall performance. Finally, the cell map visualization shows how coverage quality naturally declines with distance, emphasizing the importance of advanced techniques like beam forming and small cell deployment in 5G system. In conclusion, this MATLAB simulation successfully captures the technical advantages of 5G over 4G, demonstrating faster speeds, lower delay, and more reliable performance under the same signal conditions. It gives a clear picture of how improvements in modulation, coding, and network architecture directly translates into real-world benefits, supporting next-generation applications that demand high bandwidth, low latency, and dependable connectivity. Through, through this experiment, we can truly see how 5G technology represents a significant leap forward in the evaluation of wireless communication.